I think we'll talk about this right now, this calculator stuff. So let's see here. Uh-oh, this isn't going to work. Or maybe this is off. There we go. Okay, don't write this down, just watch. If I have log base 10 of, I don't know, 200. This, if I do equals x, I get 10 to the x equals 200. Right? 10 squared is 100. 10 cubed is 1,000. So it's somewhere between 2 and 3. And we saw this yesterday where you could estimate, but you can't solve it with the ways that we've done so far. So on your calculator, if you have one like this, you have two log buttons. You have this one. I'm not going to show up very well. That one in the top right, which has, for mine, has two little rectangles. Okay? And that one will calculate anything. Log base 2 of 8 should be, thank you, 3. That's the one you're not allowed to use yet. Occasionally, in the question on the practice yesterday, was it question number 3 or question number 3 maybe, that I said to skip? You can go back and try it now. This button, log, by default, the standard typically is when it just says log. So if I do log of 400, it means log base 10. So when I go log base 10 of 200, I get 2.30102 and so forth. But if I do log of 200, I get the same value. So that log button means base 10. But it doesn't work for other bases. This one does, but we're not doing that yet. This one, and a lot of you have a calculator that just has one log button on it. If your calculator doesn't have a log at all, you're going to need a new calculator for this unit because you will be requiring to use it at times. Okay, and so you need a log button, and it's always log base 10. I have seen computer software, computer programs where the log, when you just type in log, the default's not base 10. It's base of a special number, kind of like pi that you've not learned about yet, but it's almost important in the world as pi. And it's based on a special number that you will learn about in calculus if you're taking calculus. And so if you typed log of 200 in, you would get something different from what we got there because it's in a different base. And you would hopefully know enough about this stuff that you'd like. When I discovered it, I was like, that's not right. What's happening here? Oh, it's using this other number. So there are things in the real world, but I've never seen in the world that use other bases as a standard, but I've never seen a calculator that does it. So if you type in log of 200 and you get something other than 2.3010, come and tell me later. And if anybody ever has a calculator like that, it'd be good to know. Okay, so that's just a kind of a note from yesterday that if you are ever required to use your calculator, the log button on your calculator is base 10 by default. And then, like I said, if you have another log button that you can change the base, you will be able to use that eventually. But the one with just the log base 10, it will do you just as good. You don't need a calculator fancier than that. There's a very simple way of getting around it. It's a great little formula, and we'll learn about that on Monday. You're good? Quick little summary from yesterday just to get our minds on track. And for anybody who wasn't here or anybody who wasn't comfortable or anything like that, how do I rewrite this? Log base 2 of 8 is saying the same thing as what is the exponent I would put on 2 that gives me 8? And we know it's 3. I'm rhetorical. We know that's 3, and we could solve this just by saying it's 3, or we could do it the grade 11 way by writing it in the same base, all that good stuff. Yes, we can do all of that. But this is what a logarithm means. This is what we need to know. Remember, I used this analogy yesterday. So I think of logs as asking a question. Hey, what's the exponent you put on the base of 2 to give you the argument? That's what it means. Okay? And so this is the big part of the language that we're trying to learn right now, and getting used to this notation and used to what a logarithm means, how they work, that kind of thing. So we're going to talk about some different log properties. We're going to explore this in a bit of a different way. For most of these, we're going to rewrite them. There's only a few of them. Well, there's a bunch of other stuff we're doing, but there's only a few of these. The first 3, we're going to do them by rewriting in exponential form, thinking about it, but then coming up with a rule or a property that, like this is just for A, which means it would work for any value, right? Any number. So how would I write this? If yesterday this was an X, we're not going to do that. Don't write that down. What if it's just like some kind of a blank? It would look like this. Don't write anything yet. It would be A to some exponent equals the argument, which is A. So what we're doing here is by inspection, by common sense, by deductive logic, we're trying to think, what would I put in this box to make the left side equal the right side? My argument is just A, and my base is A. What does this evaluate to? A to some exponent has to give me the argument. Max? It's 1. So if I put a 1 in here, I get a 1 here. So this one goes there. I just want people to understand where this came from, but that's the property. This was us discovering the property. That's the property. Log base A of A is 1. Log base 2 of 2 is 2. Log base pi of pi is 1. Sorry, I said 2. It should be 1. Oops. Right? It's always 1. That make sense? Okay, good. Next one. So same thing, we're going to say A to some exponent equals 1. 0. So log base anything of 1 is 0. I think we talked about this yesterday, but it didn't have an A there. It had a 1 there. So this is a property for all values. And log base anything of 1 will give you 0. Again, this is one that pops up. Perfect example of the kind of question that would be on a no calculator quiz, because you certainly don't need a calculator if you know this property to find this, right? This one, even if the numbers were huge, you wouldn't need a calculator to solve this if you know the properties. So this is what I'm saying. The no calculator quiz is all about properties. The numbers won't be too big, but you'll have to understand properties and apply properties, stuff we did yesterday, the stuff we're doing today, some of the stuff we do Monday to solve these things. Make sense? So remember how we're doing this. We take the base and we write it to some exponent. We actually saw this one yesterday, but again, we didn't do the general case. And I tried to kind of illustrate it to you, but maybe this illustrates it better. And now is when we really need to know this. I take the base and I'm writing it to some unknown exponent. What is the exponent I would put on the base if I want it to equal a to the x? And if the base is the same, if it's the same, Isaac, it's x. And we were using this yesterday. Again, this is the property. Log base a of a to the x equals x. We were using that yesterday to solve these. So we kind of know that one, but there you have it. And it's important, if you don't really understand why, I would take some time and think back on it to make sure until it clicks like, okay, yeah, now I get it. It's just by inspection, but it makes sense. If this is a to the x, this has to be a to the x. And this is asking, what exponent do I put? Remember, it's just like this. Log base 2 of 8 equals. What exponent do I put on the 2 to turn it into this? So it's got to be 3, right? It's got to be 3. Last one's a bit trickier. This is the one where we are not going to rewrite this in exponential form. It's already in exponential form. We're going to rewrite it in logarithmic form. What's the key? Let's see if you can get this. What is the phrase I said yesterday that above all things you should remember? And if you remember this phrase, you will, and I banged on the table, you will be able to figure out most of this stuff or some of this stuff at least. How many people think they remember the phrase? Remember the banging? Okay, good. Okay, good, a few. The base stays the same. So this is log base A, and the other two parts change places. So log base A of something equals the exponent, which is log base A of x. Tyler? It's x. This is a funny one because it's going to be on a quiz or a test at some point. We'll ask you it once. And people look at it and they go, I have no idea what that question's even asking. But the answer is just right there. It's just x. These two things will be the same. It'll be like 2 to the exponent log base 2 of 7. It's 7. It's a free mark. And people go like, oh, I think it's 2 to the 7. I think it's 128. Or 7 squared is 49. Like people come up with all kinds of crazy things. And it's like, no, that doesn't make any sense. So just try to recognize, oh, this is that weird one we did, right? It's just that other number. I don't know if that's how you memorize it, but like there's a couple throughout in the practice throughout the next few days. Make sure you remember and you get it because it'll be a free mark on a test. It's an easy question every single time. Any questions about this? All right, very good. Now we're going to do some exploring. This is going to be fun. We're going to do this question in 2 different ways. One of the ways is the ways we already know. The other way we're going to see if we can figure out together. See if we can come up with a property here. You know how there's properties for the exponents and powers? You know the exponent laws? Somebody tell me one of the exponent laws. Okay, good. So you're ahead of the game. So what's the actual rule? When you're multiplying powers with the same base, you can add the exponents. Remember those? Do you think there's rules like that for logarithms? No, probably not. I wonder if there are. So let's try. Maybe there won't be. Maybe this will all be just a waste of our time. What? You don't think so? Okay, so remember when we just say log, what's the base? 10, thank you. So this is log base 10, but we don't have to write it. We get lazy and we stop writing it. We just write log. And we already got, this is that rule that we were just talking about. So it should be 10 to the 5, good. And what should that work out to? By our properties that we've been working on? 5. Okay, don't anybody shout anything out here because I want everybody to have a chance to think through this. It's a little tricky. This is how we're going to do it. It's a bit unconventional as well. I'm going to break this up into 2 parts and we'll see if there's a relationship. So instead of doing the logarithm of the product, what if I did the logarithm of each part individually? So I'm doing log, again, base 10 of 10 squared. And I'm just going to leave this blank because we don't know even if there's a relationship. Log base 10 of 10 cubed. So what is log base 10 of 10 squared? It's okay to shout this one out. 2. Sum operation. Log base 10 of 10 cubed is 3. Why are you smirking? And what should this work out to based on what we've already done? 5. Okay, here's the tricky part. Don't say anything. Can anybody think of some operation that we can put in between these 2 values I know it's hard, but that would make it work out to 5. Just try, trial and error, try some different things. Dividing, I don't know, reciprocal maybe, cosine. Roberto, what do you think? Double minus. Otherwise known as adding. Very good. So looks like the relationship here is adding. In other words, when you're taking the logarithm of a product, it's equal to the sum of the two logarithms. Okay? And we're gonna use this in a couple of different ways throughout the rest of the lesson. Try this one on your own. It works out the same way. We'll do it the same way. What's the rule for dividing powers with the same base? So this is going to be 10 to the 9 minus 6. And so same thing, you're subtracting. Yep.
Why are you assuming that it's just base of 10?
That's the standard.
So anytime it doesn't have a base, it's just 10.
Exactly. As a standard. They could have made it anything. They made it 10. Log base 10 is a common base. When you start looking at applications of logarithms, most of them are in base 10 or in base this other special number that you'll hear about later. Those are the two common ones. Okay, so this one is you're subtracting. And you can kind of see why this would work. We're going to prove these tomorrow, but you can see why it would work. I end up subtracting the exponents here, so obviously I would subtract here, right? And it gets the same idea. Okay, we got one more. This one's a little bit different. How can I rewrite this in exponential form? Two to the x equals 7. Everybody okay with that? If I wanted to rewrite this, because can I do 2 log base 2 of 7 cubed? Can you turn a 2 into a 7? Not easily. Not with a whole number. Right? If it was an 8, it'd be 2 to the 3. That'd be fine, but it's a 7. Do we have something I can replace the 7 with? I could replace it with an A. Is that what you said, or 8? Yeah, we can't do that. That would change the question. That would make it easier. You're right, but do we have something that's equal to 7? 2 to the x says so right there. This is 7. That's 7. So what if we rewrite this as log base 2 of 2 to the x all cubed? Because this is 7 now, right? We said this was 7 from the last one. How can I simplify this with an exponent law?
Log 2.
Log base 2?
Yeah, log base 2 to 2 to 3x.
Right. So when you're taking a power of a power, you multiply the exponents. So what do you think?
3x.
3x equals, what do you mean by that?
It's a decimal, so I just assumed you divide
How'd you get 3x?
because they're the same base.
So you're just evaluating this.
Yeah.
Yeah, log base 2 of 2 to the anything is the anything. But this is equal, what is x again? No? Well, it might be, yes, but it's this. So this is 3 times log base 2 of 7. Log base 2 of 7 cubed is 3 times log base 2 of 7. Imagine yourself, does it matter that it was 7? Does it matter that it was 3? Does it matter that it was 2? We're going to prove this again tomorrow, but this is almost a proof because those could have been any numbers. We didn't actually evaluate anything. So it turns out I can take the exponent on the argument of a log and bring it out front and multiply. This is a huge big deal for logarithms, and it is one of the main reasons why they're so powerful and so common in mathematics. Logarithms are used in lots of different places because of this property in particular. I just took something in an exponent and brought it out of the exponent, brought it out front, multiplied by it. Really, really useful. You'll see today why it's so useful. Were there questions on that? I thought I saw a hand. Yeah.
Well, like, is two x, is it always equal to 7 then?
We started with this statement.
But, so that's like one question in total.
Yeah, this is all considered together. If x is log base 2 of 7, and then we want to evaluate log base 2 of 7 cubed, like this would just evaluate some decimal. You could use your calculator if you have one of those buttons to figure that out, right? Go ahead.
So you took 7.
So we just did some replacing. 7 is 2 to the x, so I replaced the 7 with 2 to the x. Don't worry too much if you don't need to follow, like you don't need to memorize all these steps. We're noticing a property that we're going to use. I replaced the 7 with 2 to the x. I used a property of exponents to simplify that. Then I just evaluated this log base 2 of 2 to the anything is the anything. Then I re-replaced this in for x. And just notice that it brings the exponent out front.
So is the first part supposed to equal the last part?
No. Sorry, the very first part.
Like is log base 273.
So this equals that. Yeah. Say again. Log base 2 of 7 cubed, and then 3 times log base 2 of 7 should give you the exact same answer. Did they? Okay, we can look at it after. Probably just typed one in wrong or something. This is that property we were just using, but in reverse. Does anybody know what log base 5 of 10 is? Some decimal. 5 to the 1 is 5, 5 squared is 25, 10 is between them, so 1 point something. So we don't know what that is. Does anybody know what log base 5 of 12.5 is? Some nasty decimal. Do it on your calculator, is fine. Some terrible decimal. But when you take the log of the same base, when you add 2 logs of the same base, you can take the log of the product of the arguments. Does anybody know what 10 times 12.5 is? 10 times 12.5. I know, you're going ahead. 125. You can do that in your head. It's just moving a decimal. 125 is a power of 5, the third power. So this equals 3. So we took 2 answers. Now it was obviously set up to work out, but we took 2 answers that we couldn't do in our head, turned it into something that we could do in our head. Convenient situation, set up to work, but you can see how this can still be helpful. It's also just really helpful to be able to take 2 things and write them as one. We've seen that all over the place in mathematics, how that can be useful. If you have variables in there and you're trying to solve something and you've got things that are added, it's often easier to put them together.
No, never mind.
Same thing when you're subtracting 2 logs with the same base. You can take the log of their quotient. Does anybody know what 54 divided by 2 is? 27, thank you. Look at that. What a coincidence. It worked out again. So that one's 3. Oh, this one's so cool. Stop me if you have any questions. Otherwise, we're going to keep trucking forward. We've got a lot of examples to do today. We're going to do this one 2 ways. Whenever you have a radical, cube root, square root, fourth root, we have so many rules, laws, properties that work with exponents, we always want to rewrite this in exponential form. So the cube root of something is the same thing as that something to the 1/3, isn't that right? Remember that property we just learned? How logarithms take the exponent out front. So this is 1/3 times log base 2 of 8. So that's the one we were just exploring. That's how it works. Super powerful. So what is this? This is 1/3 times 3, which is 1. The other way we could do it the same way as we were doing yesterday. This is log base 2 of 8 to the 1/3. The other way that you might solve these is like this. So it's 2 cubed. What do I do here? Multiply the exponents. 3 times 1/3, which is log base 2 of 2 to the 1, which is 1. So same answer, works out in both ways. This is almost as good of a demonstration of that property as the last one we did, because look what happens. You end up multiplying 1/3 by 3 or multiplying 1/3 by 3. Like no matter how you do it, it's the same thing. So of course it makes sense to take that exponent and write it out front. But it's so useful for 1 if the exponent's an x. But for 2, even if it's a fraction and it's something nasty like that, I can take it and leave it out front and deal with it at the end.
Do you know when logs were created?
I do not off the top of my head know when they were discovered. There's a whole, we don't have a lot of time today, so I can't get into this too much, but there's a whole argument on whether math is discovered or created or invented. Some people think math exists and it's just discovered. And some people think that humans, mankind, whatever you want to call it, created math. Yeah, it's a whole discussion on it.
Does it even matter like what way you write it?
No. But you want to know all these different things. Some questions might be easier one way and some might be easier one way. Some questions we need that last property, some we don't. Okay, same thing. We can do this one two ways. I'm going to do it quickly because these ones are all kind of just demonstrations of these properties. Are pretty simple. Does anybody know what 4 to the 3 is? Two times 64 is 128. What power of 2 is 128? Good, 7. So this is 7. What's the other way that I could do this? Yeah, I could. That's kind of similar to this one, but you're right, I could. That would just get rid of doing the 128 thing. What's the other way I could do this, though? Yeah, turn it into that, use that property where we add. So log base 2 of 2 plus log base 2 of 4 cubed, which is log base 2 of 2 plus log base 2 of 2 squared to the 3. Base 2 of 2 to the 6, which is 1 plus 6, which is 7. Now, I wrote out extra steps. This one had more steps, but the numbers were way smaller. Again, that's the power of logarithms, is it takes the big numbers and allows us to work with them as smaller numbers. Oh, what in the world? How are we going to solve this one? It's 17. Remember, I just talked about this one, how nobody will recognize it and everybody will say, I don't know how to solve this one. It's just 17. We just talked about this. See how easy it is? You all thought you wouldn't fall for that trap. You're all like, nah, that'll never happen to me, Mr. Belair. I'll recognize that question. And like 10 minutes later, we're all like, oh, I don't even understand what that question's asking us. It's just the one that it's the other number. Okay? Watch for it when it comes up on a quiz. I think we have enough time to do a few of these. This first one's really simple. It's just a warm-up. You can go ahead and try it. The instructions say convert to an exponential equation, so that's what you're supposed to do, right? Ooh. Could you figure it out? What power of 3 do you know up to? You should know one more than that. What's 3 to the 4? What's 3 to the 4? 81. That's a good one to know, up to 81 at least. And this is, you might be able to figure out this is 3 times 81. This is pushing the limits of what I would ask you to do on a quiz. I think if your back was to the wall, you could figure this out. All the ones on the quiz will work out as whole numbers. So if you can do 27 times 3, you'd get 81. If you can do, like 8 times 3 is 24, so it's got to be 2, right? Like you could kind of, so anyway, yes. This is 3 to the 5, therefore x equals 5. What about this one? This is 8 to the x equals 16, but wait a minute. I cannot rewrite 16 as a power of 8. So what do I do? This is from grade 11. Adam? Isaac? So yeah. And?
I think it'd be 15.
Yeah, and what else?
It's 15.
Write them both as powers of 2. Good. So when you can do this, this works fine.
What I was gonna say, I don't know if you can do this, is can you do like log 8 and then in brackets like 8 times 2 and then solve like that?
8 times 2.
Yeah, 8 times 2. And then you can like, I don't know.
Yeah, it'd be 3 plus 1. Yeah, that would work. That's not what we were trying to do. But yeah, very good. I like it. What am I doing here? So this is 2 to the 3x equals 2 to the 4. Therefore, this is why these ones are a bit trickier, because it's not just x equals, it's 3x. Okay, and then I get x equals 4 to the 3. 4 over 3, sorry. I don't know if we need to see more of these. Why don't you try that one? So again, these are both going to be written in the base of 2. What is 1/8 as a power of 2? Negative 3. People think they're so smart when they can solve these things by inspection, and then all of a sudden you get one that's a fraction, you're like, oh yeah, can't do that one in my head. So it's nice to have some skills and some steps to solve the rest of these. All right, there's one more. You can look it up online. It's just, it had a radical in it, so it was just, I think it's just rewriting things in a bit of a different way, a bit more practice of some of those laws and properties. But let's get to these ones. Solve each of the following by taking the log of both sides, round to 1 decimal if necessary. Because I just want to do this one before we do, yeah. I decided to change it, that's all. Another thing you might find about logs as we work through this is there's different ways that you can solve. I mean, I already showed you that there's 2 ways to solve some of those different ones. Logs are a lot like that. I could use this property or I could use that property. So you may get a preference of how you want to solve these. But taking the log of both sides is, it's 6 of one, half a dozen of another. It's the same as rewriting in logarithmic form, so more or less. But it's another phrase that we use a lot. We take the log of both sides. And it doesn't matter what power you take the log as, but it's got to be the same, or sorry, what base? It's got to be the same base on both sides. We're going to use 10 for now, always, because that's what our calculator does. So everything we do will be base 10. But you could pick any other base. So starting on Monday, when we learn a little bit more about this, you may choose different bases in some cases, but for now it's going to be base 10.
To solve with a different base, can you divide by like the log of that number? Like,
let's get to that on Monday, but I think you're on the right track. Yeah. So log base 10, I'll write this again once and then we'll stop writing it, of 10 to the 4x equals log base 10 of 1,000. So log base 10 of 10 to the 4x is 4x. And 1,000 is 10 cubed. So 4x equals 3, and x equals 3 over 4. So that one worked out nicely, but not all of them will. We didn't in that case because everything we did used a property or like a step that we've done.
Would you lose marks if you just did like, instead of putting log in front of it, you just made that 10 to the 3 is equal to 1,000? And you did like the grade 11 one?
Okay, so that's like what I'm saying. There are different ways. You could rewrite it in logarithmic. Oh, I see what you're saying. Yes, because this says solve each of the following by taking the log of both sides. So you would have to follow those instructions. But Adam, I wouldn't worry. And nobody worry about that right now because we're just exploring different ways of solving these. You want to have all these tools in your tool belt. In general, your answer to that question is if you think that's the most efficient way to solve, then yeah, you could solve it that way. Can you solve this one like that? No. So we need another way of solving these. And right now what we're doing is taking the log of both sides. So this is log base 10 of 10 to the x minus 5 equals log base 10 of 50. So log base 10 of 10 to the x minus 5 is x minus 5. Right? I'm going to isolate by adding 5 to both sides. And then I'm going to do this on my calculator. Try yours. Because remember, our calculator has the log button. Said round to one decimal place, so I got 6.7. Okay, a couple more. So that last one made some sense to do it as base 10 because it had a 10 in it. This one doesn't, but it's still going to work to take the log base 10 because that's what our calculator does. So we take the log of both sides, and I go log base 10 of 7 to the 2x equals log base 10 of 2,500. What can I do in the next step? The last one, I'll show you what we did. If this screen will move over. Oh, it doesn't want to. Is we said log base 10 of 10 to an exponent equals the exponent. So that was useful. And we can't do that this time. So we need to use a different property. What is it?
Okay, why can't I use
Because it would have to be log base 7 of 7 to the 2x. Remember when I said there's a property that's so powerful? Exactly. Look at that. No exponents left. That's that property that we just explored. And this is what I'm saying is we explored it and we did all this stuff. You don't really need to know all that stuff. You need to know this. You need to know that it doesn't matter what the base and the number is, that logs take exponents and bring them down. This is huge. Huge. And now how do I solve this? I get 2x equals log of 2,500 over log of 7. Divide both sides by 2. So this is log of 2,500 over 2 log 7. And I'm going to do it like this. log of 2500 over 2 log 7. 2.01, so 2.0.
So would we so the winning questions like this on the quiz? 'Cause
That's exactly right. Good question. This type of question would not be on the quiz. You can't do it. You can do everything up until the last step with a calculator, but you need a calculator for the last step. Unless I'm in a really bad mood, then maybe. Bang.
What is the difference between the one yesterday and the one before?
The one before was log base 10 of 10 to the x minus 5. So I used a different property to say that's equal to x minus 5. This one, I took the exponent out front and then had to bring that log over because it was log base 10 of 7. We can't evaluate that in our head. That's the difference.
So, okay. I just got confused because it looks like that's log 10. And then
Remember what I said, when you don't write a base, it's base 10 as a standard.
no, but I thought the 10 was the base.
Well,
Can you, can we just like write it that way?
you can write it however you like. But I would say, like that's why when you write the base, it's supposed to be down low. So if you look at all my, like maybe people don't write it that way and some people don't, but if you look at all of mine, if I can find one, like it's always written way smaller down below the G and this one's big. You know what I mean? Get used to writing it the right way. All right, where's that question we were working on? There, last one of the day. You can go ahead and try this one. Take the log of both sides. What's next? Keep going, don't wait for me. So I brought my exponent, the negative x, out front, multiplied it through by the log base 10 of 15, divided both sides by log base 10 of 15, and then brought the negative over so I can do it all at once in my calculator. So negative log of 2 divided by log of 15 equals, did anybody else get negative 0.25? So that's negative 0.3. Awesome.